You'll sometimes hear people say that group theory is the study of symmetry. In this video we're going to look at some examples of groups which really are built out of symmetries, namely the dihedral groups. So here's the definition. We take a regular n-gon xn in R squared, whose centre is at the origin. And we usually also insist that one of the vertices lies on the x-axis because it happens to make the calculations a little bit more convenient. The dihedral group D2n is the group of all reflections and rotations of R squared which leave xn fixed setwise. So that means the points within this n-gon might move around itself, but the whole n-gon is left in the same place. The group operation on D2n is composition of functions. So a regular n-gon has n rotational symmetries, counting the identity as one of these rotational symmetries, and n reflectional symmetries. So its size overall is 2n. To make this dihedral group a little bit more concrete, it helps to think about these rotations and reflections as the linear maps which they are, because that means you can represent them using matrices with respect to the standard basis. At the bottom of the slide here, I've copied some of the useful standard matrices for rotations and reflections. The matrix r theta here represents an anti-clockwise rotation about the origin through theta radians. So what that means is that if you have a vector x and you multiply it by the matrix r theta, the result is this vector x rotated anti-clockwise by theta radians. Similarly, s theta here is the matrix for the reflection in a line which makes angle theta with the x-axis. If you're wondering where these come from, well, it's actually very easy to work them out for yourself with just a little bit of geometry, as long as you remember what the matrix of a linear transformation actually tells you. The first column of these matrices is telling you about what happens to the first standard basis vector. And the first standard basis vector is a unit vector in the direction of the x-axis. Similarly, the second column tells you about what happens to the second standard basis vector, which is a unit vector, by unit I mean length 1, in direction of the y-axis. So if you want to work out these matrices yourself, then you can do it just by working out where would an anti-clockwise rotation by theta radians send a unit vector in the direction of the x-axis, and where would it send a unit vector in the direction of the y-axis. When you've worked those out, those will be the two columns of this matrix, and you'll find that these really are what you get. And of course the same thing applies for the reflection matrix as well. So let's make one more comment before we go and move on and look at a concrete example of a dihedral group, which is that you can say something about powers of these matrices. So if I do a rotation by theta, and then I do a rotation by phi, well, of course, that's the same as doing a rotation by theta plus phi. Let's draw that phi a little better. So the rotation matrices ought to obey this property, and in particular, if you do r theta to the power n, well, then you're doing a rotation by theta n times, so you ought to get r n theta. So if theta is 2 pi divided by n, for example, then you will get a rotation matrix with order n. And similarly, if we think about these reflection matrices, we think about what should happen with s theta if I square it. Well, if you do a reflection twice, the same reflection twice, then everything should be back where it started. So this should be equal to the 2 by 2 identity. So again, if you're not really sure about these matrices, they really ought to have that property. And if you check them, you'll find they really do. Okay, let's move on to looking at the example of D6. So D6 is the group of reflections and rotations of a regular 3-gon, that is, of an equilateral triangle. As I said before, we usually insist that one of the vertices is on the x-axis, and that's how I've drawn it on this slide. The reason for doing that is because if one of the vertices is on the x-axis, then one of the reflective symmetries of this equilateral triangle will be reflection in the x-axis, and that has a very simple matrix, so it's easy to use in calculations. So we'll begin by thinking about what the rotations are, what the rotational symmetries of this regular triangle are, of this equilateral triangle. So there should be a rotational symmetry which rotates through 2 pi over 3 anti-clockwise about the origin. And we'll give a name to that, we'll call that R. And then the other rotations are a rotation of 4 pi over 3 and a rotation of 0. So those things will be the identity, and then R squared. So those 3 rotations of this regular triangle are given by the identity r to the 0, and then r squared. So the other thing to notice about this diagram is that I've labelled the vertices of this equilateral triangle. That's to make it easier for us to figure out what's going on when we do several symmetries and we want to know what's the result of doing a composition of several different symmetries. We can keep track of these vertices and that will help us figure out what's going on. So for example, let's draw what would happen if we did R. So if we did R to this, then what would the triangle look like? Well, it still looks like a triangle, but now 1 has rotated through 2 pi over 3 anti-clockwise, and 2 will be down here, and 3 will be over here. Okay, let's now bring in some reflections. So we're going to give a name to one reflection first of all. So S will be reflection in the x-axis. So another way to express this will be reflection through a line through the vertex 1 and the origin. So reflection in a line through 1. So what's going on here is we'll just label it in the diagram. S is reflecting in the x-axis. So S is sort of swapping the positive y and negative y parts. So what would happen if we did S? I'm going to draw this arrow to show what it would look like after we did S. Well, S would fix the vertex 1. That would stay where it was, but it would swap 3 and 2. So that's what would happen if we did the reflection S to this triangle. So let's now think about some other reflections. There ought to be 3 reflections: a reflection through the vertex 1 and the origin, or through a reflection in a line through the vertex 1 and the origin, and in a line through the vertex 2 and the origin, and in a line through the vertex 3 and the origin. And I claim those things are given by the compositions SR and SR squared. So I want to see why that is. Now, of course, SR, if this thing really is a group, SR must be some symmetry of this triangle. So it must be one of these reflections or rotations. And I claim that actually SR is the reflection along in a line through the vertex 2 and the origin. And let's see why this is. So we're going to look at the symmetry SR. And you'll remember that the group operation is composition of maps. So SR means do R and then do S. And we know what happens when we do R. We end up with a triangle in this configuration that I've drawn right here, where we have the 3 on the right and 1 at the top and 2 at the bottom. So let's think then what would happen if we did S to this. So if we're now going to do S and see what happens. So this is my arrow symbol to say we're doing S to this. Well, we do S. We fix 3, because S is a reflection in the x-axis, and we swap those other 2 positions. So what it will look like is this triangle here. Okay, looks like that. And if you look at it, then that is what you would get if you reflected on a line through, if you reflected in a line through the vertex 2 and the origin, because you see 2 would stay fixed and you'd swap 1 and 3, and that's exactly what's happened in this picture, illustrating what happens when we do R then do S. So this is reflection in a line through 2 and the origin. So if you find this not very convincing, then what you can do instead is simply multiply the matrices. So you know a matrix for R and a matrix for S, so you can multiply those matrices together and you will see that you get a reflection in the line that I claim you get a reflection in. But I mean, this is actually perfectly rigorous, because if we have linear maps like R and R times S and S times R, then those linear maps are determined by what they do on a basis of the vector space they act on. And the vectors representing the points that I've labelled, 1, 2 and 3, well, if you just pick two of them, say the points labelling 2 and 3, and then they will form a basis for this vector space. So you can completely determine what a linear transformation is by working out what it does to that basis. So in other words, working out where this composition, S composed with R, sends vertices 2 and 3. And what it does is exactly the same as the linear transformation which reflects in the line through 2. Okay, so similarly, if you do the same sort of thing for SR squared, so just work out what happens to the vertices, then you'll see that what we get is a reflection in a line through 3. So that gives us all of the elements of this dihedral group D6. There were 3 rotations, and those were the identity rotation R and R squared. And we found the 3 different reflections, and we managed to express those in a way using S, a reflection in the x-axis, and R, this rotation. So we found all of the symmetries. But of course there were lots of other products which we could do of group elements, and it's of interest to figure out what those products are. For example, we have the identity R, R squared, S, SR and SR squared. But what about R composed with S? So this is a product, a composition of 2 group elements. So it had better be one of these 6 group elements we've already seen. But the question is, which one of those group elements is it? So again, if you like, you can work out the matrices. So write down the matrix for S and R, multiply them together, see which one of the 6 matrices for the other symmetries we've already seen it's equal to. But we can also do this by keeping track of vertices. So let's do that. So we know what happens when we do S. So this should have had the label S, shouldn't it? When we do S first, we end up in this configuration right here. So let's now do R to that. So we've got RS, which means do S, then do R. So now to this, let's do R and see what happens. So R gives me a rotation anti-clockwise through a third of a turn. So I'll get 1 at the top, and then 3 at the bottom, and then 2 over here. So that's the configuration I end up in. So what is this? Which symmetry is it? Pause the video and figure it out for yourself. Okay, well, what's happened there is we have done a reflection in the line through the origin and the vertex number 3. You can see 3 stayed where it was with respect to the original configuration, and 1 and 2 got swapped over. So that would be what would happen if you reflected in a line through 3 and the origin. So RS is equal to SR squared. Or another way to put that is SR to the minus 1, because R is a rotation of order 3. It's got order 3 because it's a third of a turn. So if you do it 3 times, that's the same as doing a whole turn, which is the same as doing nothing. So RS is equal to SR squared, which is the same as SR to the minus 1. And that is going to be quite helpful when we flip to the next slide and start working out a group table for D6. So let's write down what I wrote down, what I worked out just then, so we can remember it. R times S was equal to SR squared, and of course that was the same as SR inverse. So we're going to try and work out the group table, and you can see I've filled a bunch of this in already, because a lot of it is actually quite straightforward to work out. So I've labelled the rows and the columns with, first of all, the rotations and then the reflections, and I've written the reflections in the form we first looked at them. So S, which was a reflection in the x-axis, then SR, and then SR squared. So first of all, the first row and column are always easy. Now I've written E instead of the identity here, so what I mean by this is just the identity. The first row and column is always easy because you're multiplying by the identity, so it doesn't do anything. So you just copy the row and column labels into those first columns. Next, there's something else easy happening here, which is that we can look at the first, so the 3 by 3 sub-table in the top left of this table is easy to work out, because that's just about composing rotations. And I know that, for example, R composed with R is R squared by definition, and R composed with R squared, well, that's R cubed, but as we said, R has order 3, so that's just back to where we started, so back to the identity. So this top left 3 by 3 block here is nice and easy to work out. And also it's actually telling you something, isn't it? Because it's telling you that the rotations form a subgroup. So if you just look at the rotations in D6, those form a subgroup of order 3, consisting, in fact, it's the cyclic subgroup generated by R. So let's look at some other easy parts of this group table. So which other parts can we work out without doing any work? So what can I do? Well, if I look at the bottom left block, so I'm going to look at this block in the bottom left here. This one is also quite easy to write down in terms of the group elements as we've put them in the rows and columns. Because if you do S times R, that's one of the things we put in there. So we can put SR here. That's just because the thing in row S and column R is by definition S times R. And then of course here we have SR squared. So that one's easy too. Then in the row below that, SR times R, again that's just SR squared. Nothing to think about there. And SR times R squared will be S times R cubed. But R cubed is the identity, so this is just S. And then on the bottom row here, SR squared times R, that's SR cubed, so that's S again. And then next we'd have SR to the 4, and because R cubed is equal to the identity, R to the 4 is equal to R. So here we have SR. So the interesting things start to happen if we look at the top block here. So we'll look at this block in the top right hand part of this group table. So in the second row here, this entry in row R and column S is R times S, and we figured out on the last slide that R times S was SR squared. So it would be, I guess technically correct just to write RS in here, but it's not really the spirit of the game, and we'd like to know which one of these six group elements, as we've written them in the rows of columns, this is equal to. And actually we know that because we know RS is SR squared. So we've already worked out that what goes here is SR squared. We can actually use this to help us work out what the next entries in that row should be, because the next entry in that row should be R times S times R. So RSR should be equal to, well, that's RS multiplied on the right by R. So that's SR squared R, which is SR cubed. So that is S again. So I can put an S here. And finally, well, actually, if you've done one of the unassessed questions, I think on sheet 4, or then it might be on sheet 5, you'll know that group tables have this Latin square property, which means that every element appears exactly once in every row and every column. So actually we could just say, well, there's only one element left over, so it absolutely must be SR, which goes in this last entry. But let's try and work it out, imagining we forgot about that nice and useful relation. So what we want to know in that last entry in row 2 is what is RSR squared in terms of one of these group elements that label the rows and columns. So R times S is SR squared, so I'm going to substitute RS. I'm going to put SR squared instead. So I'll have SR squared R squared, which is SR to the 4, which since R cubed is 1, is just SR. So we can put SR here, and as a what the engineers called a smoke test, right? Is there smoke coming out of it? If so, you know it's broken. Well, there's no smoke coming out of the second row of this group table. It really does contain each one of the group elements once. So everything seems to be okay. Of course, maybe they're in the wrong order. Maybe I made a mistake and they're in the wrong order. We can't tell that, but we can at least tell that there's nothing that has been repeated. Okay, let's do the next row. So we now have to work out things like R squared times S. How can I do R squared times S? Well, I could think of this as R times S, because what I really want to do is move the R's over to the right, and I know how to move an R through an S because of this relation here. So what do we have? R squared S is R times S, which is R times S times R squared. Now I want to move that S over to the left again, so I can just substitute again. R times S is SR squared, so this is SR squared R squared, which is SR to the 4, which is SR because R cubed is 1. So here we get SR r, and I'm feeling quite happy because I don't have any repeats in the s column or in the r squared row yet. Okay, so we could do r squared times sr, and I'm going to leave you to work this one out. R squared times sr, well, it will turn out to be sr squared, which you should check for yourself, and there should be an s there. And there is a bunch of other calculations that we need to do as well. So in this bottom right section of the group table, so let's just record that. What did it turn out to be? R squared times SR turned out to be SR squared. And in the bottom right part, well, we'd have to work out things like S times S. Now I've put in some identities there because remember S and SR and SR squared are all reflections. So when you do them twice, you get the identity. So there must be an identity just here when we did S twice, just here when we did SR, that reflection twice, and just here where we did SR squared twice. So that gets us somewhere. But the ones where we have to do some work are things like, well, what have I got? S times R. Okay, that's easy. Because S squared is the identity. So I put an R here. And S times SR squared. That one's also easy because you get SSR squared, so it's just R squared. Okay, so where we have to do some work is things like SRS. What's this? SR squared. What's this? I'm going to leave you to work these out, and I will show you the answer at the start of the next video.